Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 2.2.2, which is Similarity. It begins with this problem diagram down here in problem A. It says in problem 51, you dilated triangle ABC by a factor of 2, imagining two rubber bands to create A prime, B prime, C prime. Which side of A prime, B prime, C prime corresponds to side CB, and which side corresponds to side AB? So take a second and go ahead and pause and take down this diagram onto your paper. That way you can have this diagram as well. I've already labeled the coordinates for you. And we're trying to just find corresponding sides. Remember, corresponding is when the pieces are in the same position but a different location, they serve the same role. It's hard to see sometimes with this diagram. So whenever I have a triangle inside of itself, what I like to do is I like to draw two separate triangles. So this is A, this is a C right here, and this is B right here. So that's the smaller triangle. And then the larger triangle really is its own entity, right? It really is its own thing, where this is A prime, C prime, and B prime. Now it's pretty self-evident where the corresponding sides are going to be. So if I wanted to say side CB, well, that's the vertical side right here. He would be correspondent to, C prime, B prime. And then AB, which looks like the hypotenuse of this right triangle, would be corresponding to A prime, B prime. And so again, you're just trying to find those corresponding sides right there. And let's go ahead and take a look at the relationship of the corresponding sides. Write down all of your observations. So let's see. If I wanted to find out the lengths of each of the sides, I could go ahead and use the Pythagorean Theorem on everything. And so from here, if this guy is 3 and this is 4, okay, then by use of the Pythagorean Theorem or by knowledge of Pythagorean triples, I could do 3 squared plus 4 squared equals c squared, and then that becomes 9 plus 16 equals c squared equals 25, so c equals 5. Now, you could have known that using a Pythagorean triple, 3, 4, 5. This A prime, C prime here is worth 6. The B, C is worth 8. That makes me start questioning a relationship right here. From 3 to 6, from 4 to 8, that gives me pretty reasonable expectation that the 5 would get me a 10, but let's not take our word for it. Let's go ahead and find out for real. 6 squared plus 8 squared equals c squared. So I've got 36 plus 64 equals c squared. C equals 100. Oh, sorry, c squared equals 100. So that means that c equals 10. And here we are, right? We predicted it would be 10. It was 10. So we know that, so some of the observations we can say is we can say that each side length, each side is double the length of the original. So that's one observation. Another observation is that each side maintains its original slope. That should make sense, right? I mean, it's not like the line deviated as we expanded it. These two lines are vertical. The BCs, the ACs are horizontal. The AB and A prime, B prime have the same slope. Now, that's going to play a big role in the next observation. And if you had a protractor, you'd probably be able to see it, is that all angles are equal. Now, here's what I'm not saying. I'm not saying that all three of these angles are equal, but what I'm saying is that angle A is the same measure as angle A prime. Angle B is the same measure as angle B prime, and angle C is the measure of angle C prime. So it's not like I probably should reword that. Instead of all angles are equal, I should say corresponding angles are equal. Corresponding angles are equal. I think that will be a little bit more clear as to what I'm trying to say there. Moving on to part C here, it asks, Why does side A prime B prime lie directly on AB and A prime C prime lie directly on AC, but B prime C prime doesn't directly rely on BC? I mean that should be relatively obvious. It's hard to say what's obvious and what's not, but it really goes down to the point of dilation being in the origin. The point of dilation is at the origin, and AB and AC, side AB and side AC, pass the point of dilation, pass through the point of dilation, but side BC does not. Now, again, that should be relatively obvious, right? I mean, like, if you look at how the triangle is being expanded, it expands out this way, but why would these sides suddenly be on top of each other if the diagonal and horizontal sides are growing outwards, right? The vertical side would grow out and extend past its original side. So I think that's hopefully an obvious question, but we can, have questions about that later if you guys felt like it. It says part D, could you determine the side lengths of A prime, B prime, C prime by adding the same amount to each side of A, B, C? Try this and explain what happened. So by adding the extra amounts, right? By adding the extra amounts, they're asking, could we obtain the side lengths? I don't think so. I mean, if we added 1, 2, 3 more, I guess we would get a total length of 6. That means that A prime, C prime would be 6 if I added 3 more to it. And then if I added 4 more, question D is asking, could you determine the side lengths of A prime, B prime, C prime by adding the same amount to each side? And try this and explain what happened. So if we had to pick an amount, an arbitrary amount to add this to, let's see, to a 3, 4, 5 triangle, if we added, say, 1 to each side, so if we were to do 3 plus 1, that would be 4. 4 plus 1 would be 5, and then 5 plus 1 would be 6. If we did that, assuming we could do a 4, 5, 6 right triangle, so a 4, a 5, a 6 right triangle. Let's see if that actually works. Does 4 squared plus 5 squared equal 36? So from here, let's see here, that would be c squared. So 16 plus 25 equals c squared. I don't think so. I think that's 41. So I think if we add the same amount to each side, I don't think we're going to be able to get our similar figure. Similar figures definitely grow. When they grow, they have to stay proportional. And so I believe by adding the same amount to each side does not properly convey that proportion. So I think D is going to be false on that one. So now it says Monica dilated triangle ABC to get a different triangle. She knows that A double prime B double prime is 20 units long. How many times longer is all that stuff? Okay, cool. Let's go ahead and delete this real quick, and I will come back and do it. All right, and we're back here with 2-58. It says, Casey decided to dilate her favorite letter C, of course. She dilated several C's using a copy machine. The scale factor, or zoom, tells the copier how much to dilate the figures on the text and on the paper. For example, if Casey wants to set the zoom to 200%, that's the same as a scale factor of 2. The side length of C would be doubled. If she sets the zoom to 50% or scale factor to 0.5, the machine would shrink the side in half. Zoom is often written as a percent, while scale factor is usually written as a decimal or a fraction. I will be honest, scale factor as a fraction is probably going to be more your friend. The copier doesn't change any of the angle measures, therefore the copier is dilating the figure. Again, I have to emphasize, when you dilate a figure, all the inside pieces stay the same, especially the angles as we saw in the triangle above. And so it says, part A, it says, since the scale factor multiplies each side of the regular polygon, of the original polygon, then the ratio of the widths must be the ratio of the heights. They must be equal. So we have to verify that the ratios are equal. Let's find out. So did this copy machine do its job correctly? Well, what we're going to do is we're going to compare corresponding sides for part A. And basically, I'm going to say, and it doesn't matter which way you go, okay? I'll show you both ways, but since they are moving from large to small, I'll go ahead and say this is going to be 24 over 8, and then I'll compare that to 18 over 6. Now, there's actually a few different ways you could do this. I'll probably do it all three ways if you want to. And it turns out, I believe these two things are both the same, right? This guy does turn into a 3, and this guy does turn into a 3. So we can say, yes, they did, the ratios are equal. Now, some of you might end up getting the answer of yes for a different reason. If you went the other way and said, hey, the original 8 to 24, and then went from 6 to 18, you would get 1/3 versus 1/3. But again, it doesn't matter what that actual number is. The fact that the numbers match up means that the ratios would be the same. Some of you might have even done something a little more different. A different kind of technique on this is you can compare what I call self to self, which in this case would go 8 to 6 versus 24 to 18. And again, we would get 4/3 here upon reduction of that fraction, right? They both divide into 2. This guy here, they both divide into 6, getting you 4/3. Again, notice how the ratios end up being the same. So it doesn't matter which way you do. You can go from small to large, large to small, or self to self, and it's not a big deal. As long as the ratios are the same, then the shapes are going to be proportional. And notice in part B, it says a proportion is an equation with two equivalent ratios. It says after looking at Casey's work, her brother wrote the proportion 8 over 6 equals 24 over 18, which I believe we do have. That's the deal right here. That's what we have in this portion of the work. And I believe the next part of the problem is probably telling you exactly what I just said a few seconds ago. He says, are his ratios in fact equal? And they are. And how can he show his work on his diagram? And I believe we just did that. We did B without realizing it. Sorry about that. It says, Casey decided to create an enlarged C for the floor of her bedroom. To fit it, it needs to be 72 centimeters wide, so side to side. If X is the height of C, write and solve an equation to determine how tall the C on the door must be. Okay, give me a second. Let me grab this, and we will go. And here we are with this image right here. So from here, we're going to delve into the notion of setting up a proportion. Now, I'm going to set this up all three ways. I'll solve it one way, and then I'll let you guys solve it the other two ways. From here, I will go ahead and do small to large, okay? And what I mean by that is I'm going to compare the small shape to the large shape. How do I do that? Well, I'm going to go ahead and do 8 over x. Notice the corresponding sides, right? 8 to x, and that's going to have to equal 6 over 72. So I can go ahead and cross multiply this if I want to, but it might be easier if I reduce this guy first. Now, I believe this is going to become 1 over 12, and that makes this multiplication a little bit easier. 96 equals x, and I think that is going to wrap up that problem. Now, you could have done it a couple of other ways. You could have done x over 8 is equal to 72 over 6. I went from large to small. You could do self to self. You could do 8 over 6 is equal to x over 72. I would encourage you to pause and try these two ways. Either way, I believe 96 is going to be your answer. Give it a whirl and check it out. I'm going to go and copy D and E into the problem, and we will go from there. All right, in part D, it says Casey wants to make a reduced C to wear on a necklace, and she decided she would have to make the height of the C become 2. What scale factor would she have to use to reduce her C from the original figure? So from here, I'm going to go and just draw the original figure right here, where this was 8 and this was 6. Now her new figure is going to look like this, right? Her height is going to be 2, and we would have to make this x, right? We don't know what that is. So let's go and find out what this new side would be. From here, we would have to do, let's go large to small this time. Let's go 8 over 2 is equal to 6 over x. Now notice, I'm going to go and reduce this guy to 4, 6 over x. So here, 4x on cross multiplication equals 6. Divide everything by 4. X equals 3/2 upon reduction of that fraction. Now from here, look at the proportion here. It looks like by reducing the 8 into a 2, your scale factor would be 1/4 because you have to divide the 8 by 4 to become 2. Well, check it out. If I do that to this side, I get 6 divided by 4, which is 3/2 anyway. So hopefully part D makes sense. All we did was we just shrank the thing. Now from here, what would happen if the scale factor between KC's two C's was equal to 1? Well, essentially, right, what did we do? We took the 8 and we didn't divide. We multiplied by 1/4. Well, I guess we kind of divided. And that's how we got the 2. We took the 6, divided it by 4, or multiplied by 1/4 to get the 6/4. We did the same thing here, right? In order to get the 6 to become the 72, we have to multiply by 12, right? Well, what they're asking in part E is if the scale factor is 1, that means that the sides would get multiplied by 1, and whenever we multiply something by 1, that results in no change. So if your scale factor is 1, you can expect no change to happen. Okay, hopefully this makes sense. I'll be back with the last and final problem. And here we are with 2-59. It says Roshida drew triangle ABC, then dilated through point A to create A, B prime, C prime, and all the lengths are in centimeters. It asks, why are the two triangles similar? Write a similarity statement. A similarity statement at this point in the game might be a little difficult because we haven't learned how to prove triangles to be similar, and we will learn that eventually. For now, all you have to know is that because the triangles are mapped through the same point of dilation, they would be similar. And I think that would be good enough for now. We will eventually learn how to really make statements of similarity, kind of like how we do statements of congruence, and we will do that later on. It does say, moving on to part B, it does say, Roshida then decided to redraw the diagram as two separate triangles as shown below. Write a proportion that we can use to solve for x in the using the corresponding sides. Okay, that's not bad. We can do that. We know that 4 corresponds to 10, and we know then that x corresponds to x plus 9. Now it doesn't say to solve for it, so I'm not going to solve for it just yet. But I will go and pause real quick and then move on to the next problem. Give me a second. And I just realized it did actually say solve for x. Sorry about that. It says write a proportion and solve for x. So why don't we go and do that? There's nothing wrong with that. We can go and cross multiply. There it goes again. Our good old buddy cross multiplication making its triumphant return. So 4 times x plus 9. Let's go and solve. 10x equals 4x plus 36. I'm going to go and move the 4x over, and I'm going to get 6x equals 36, dividing everything by 6. X equals 6, and we're all good. Now, the reason why I noticed that it actually told me to solve for x is because in part C it says write a different proportion and solve. And did you get the same value for x? So what I'm going to do is I went from small to large. The other proportion you could write is you could go from large to small if you wanted to, but I'll go ahead and do, just because I want you guys to know definitely that they end up being the same, I'll go and do self to self. So what I'll do is I'll go and do x over 4. Notice I'm using the same triangle. X over 4 is equal to x plus 9 over 10. And let's see if we get to the same spot here. If I cross the 10 to the x and I cross the 4 to the x plus 9, well, check it out. Look at where I am right now. Look at this yellow cloud. That yellow cloud should look familiar because I'm highlighting that yellow cloud up here on the white background in purple. So see how we got to the same spot. So as long as we stayed the course on the yellow portion of the problem, we should get x equals 6. Let's go and just make sure though. So 10x equals 4x plus 36. I feel like I'm experiencing deja vu right here. And you should as well. 6x equals 36 and divide by 6. And here we go. We have a glitch in the matrix. X equals 6. We're good. All right, so now let's find out how long AC and how long A prime, C prime are. Well, we know that AC is equal to 6. Again, we're doing part D here. AC is equal to 6. A prime, or rather AC prime is going to be, 9 plus 6, so that's going to be 15. And they're asking you, what is the ratio of the original segment of BC to its image B prime, C prime? Explain. So if we're going to look for the ratio of the segment, they're asking us for the scale factor. So from here, if this is 6 and this is 15, let's look at the scale factor. Well, we know that the scale factor is 4 over 10, or it could be 6 over 15. Either way, the scale factor looks like it's going to be 2/5. So the ratio of the original segment to its image b prime c prime, well, in this case, check it out. This 2/5 here, because I'm going from small to large, what that does is because this fraction here is under 1, it shrinks the image. So actually, to go from BC to B prime C prime, you need an enlargement scale factor, which will then become 5 over 2. And lastly, in F, they're asking us for the relationship between B prime and C prime. I mean, you could say they're proportional. They're proportional. And they're also parallel, because they pass at the same point of dilation, and they actually were part of the same triangle. So there you have it. There is similarity for you guys, and enlargement and shrinkage. Feel free to leave comments and questions in the comments area, and I will see you in the next episode.